let's recap a little bit more about waves. So let's look at these 5 areas which we're going to cover in this video. Let's start with this one first. Alright, this could be considered to be connected to number 5, but let's just explain it in terms of what are waves. And for this, I'll be actually using a 10-year series answer to help you define it very clearly. It is something that you could actually try to commit to memory, generally from either the exact words or just the idea of it. Oh, but that's a really big block of words, right? What can we understand from this is really just about that there is something that's periodic, that's moving, and I'm transferring, first and foremost, energy. Okay, but what is not being transferred is that the particles are not transferred. Okay, so remember when we talk about waves, right, really there's a transfer of energy from one place to another, but there is no transfer of the particles itself. So that's to say, right, that there will be a direction of the wave moving. So we talk about it in terms of the wave propagation or wave motion, and then there's the particle motion or particle vibration. So yeah, you could actually use such a big long answer, but the essence of it is that what's happening is that there's a transfer of energy, no transfer of the particles or the medium itself. And yeah, there might be this disturbance where things cause to vibrate and move, but please, there is the particles itself in the medium, they just vibrate, they just oscillate, and they don't move away. Alright, so that's basically what waves are. How do you represent these waves? Now, the representation would be one of the key ideas of this entire thing that you must know, because there are two ways of doing it. I can either think of it in terms of just one particle, or I can look at all the particles. But all particles, I'm only going to look at it at one point in time. So it's a snapshot. Right? For one particle, I'll be looking at it over as time progresses, as time moves on, where does that particle move? Right? So this one would be when I gave all of you that single sheet of laminate, that piece with the positions marked at each interval of time. So the intervals get smaller, right? So we had that, and for all particles is when we put all of them side by side. So for one particle, we'll be looking at a graph which is going to be my displacement time graph. And why do we say displacement? It's because this particle will be moving around, will be moving, let me use this black marker over here. Okay, let's just use it back. Because the particle going up and down is displacing about this rest position here, correct? Equilibrium position. So over time, where is it moving, right? And we can actually plot and see how is it moving. And what we did in class is that it will look something like this, right? At maybe 0 seconds is here, and then after that, you start having this pattern that looks something like this, right? Not sure if my drawing is very accurate, but generally you see something that looks like this, right? And we'll be able to plot such a graph that over time, right, at different points in time, there's a certain displacement away from the rest position where it started, right? Because if there's no wave going through it, the particle will just be staying here. Over time, there's no displacement. But now that the wave has gone through, we realize that, the particles start moving. At each point in time, it moves a certain distance away from my rest position, my equilibrium position, right? So we get such a graph, right? And that's why it sort of crosses, whereby like as if you're plotting a graph, right? So that's a displacement time graph. So we need to know a bit more about these things also, because in this, I can also see that, I can find my amplitude, which is the maximum displacement from the rest position. It could be from the rest position to my crest. It could be my rest position to my trough. So this also could be amplitude. And when I look for at this entire wave, right, for this complete cycle, this complete oscillation, what would that be? I'm actually looking at the total time for a complete oscillation, correct? So when I look from the beginning to the end for a full cycle, this gives me my period, or T. Okay. Now, what else do I know? I also must remember how I went from period to frequency. So there's period, which is using capital T. I use units of seconds, and this is different from frequency, where I use F and I use the units hertz. Okay. From what we learned in class, and using the graph which looks something like this. So I said again, try to imagine that I have 1, 2, 3 complete cycles, and this is in exactly 1 second. So this is displacement, this is time. Realize that, oh, in 1 second, then we start saying, oh, in 1 second I have 3 complete cycles. Well, that's how frequent I see it. 3 complete cycles in 1 second. This one I'll say that, oh, that means this is 3 hertz. But period is a time taken for 1 cycle. 3 cycles in 1 second. 1 cycle will be 1/3. So we say that, oh, it's actually 0.33 seconds. But in this case, you must remember, we just use the fractions. Of course, we don't use fractions in physics. Okay? But this just to help you visually remember that, oh, these two are reciprocals of each other, which means if I want to find frequency, frequency is actually 1/period. Okay? Actually this one should be 0.333 because we always use 3 sig fig. But the idea is how we go from period to frequency. Okay? Now that's for one particle. What about if we put all together, look at all the particles moving? Remember, side by side, and then after that we're getting you to shift, shift, shift. Okay? And then if we just look at one of the photos in the entire video we made, what we see is that we can actually see different particles being displaced at different positions at a different distance away from the start position, right? So again, that means there's a lot of those laminated cards side by side, and each of those things at a certain point in time, let's draw it here. So each of the particles have a certain position, and we can actually show that position. So I'm just going to use a dot, okay? So maybe this one is here. In the next card, the position is here, it's here, here, and so on and so forth. And when we put it together, then we take a snapshot of it, we will see something that looks like this. Oops, no, that doesn't look good. Let's try again. Okay, something looks like this. And what we're saying is that this is made of many particles. Okay? Well, all these particles, as the waves goes through, we see this pattern. Okay? See, this particle over here is really far from this position I started over here. Right? So there's a distance away from this particle to this particle. That's why this is a displacement distance graph. Okay? So I can still find my amplitude. I still know this is a crest. I still know that this is a trough. But now as I think of one full cycle, this whole thing right now, this thing, one cycle is not in terms of time anymore. It's not time, but distance. So this tells you really the length of my wave, also known as my wavelength. And I use lambda. Okay, it's in meters. Remember, it's really a length, and I use a symbol lambda. Okay, can. To clarify, there are many ways to find a wavelength. So let me draw a bigger graph. That's also displacement distance. but instead of just one cycle, I can draw more cycles. Okay, assuming that my diagram is drawn accurately, a wavelength could be from this crest to next crest because that's one cycle. It could be from this trough to this trough because that's one cycle. And also, I could say, if I'm starting from here, well, where's a full cycle? So to here, is that a full cycle? No, right? Because if I loop it, it just go here, 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 here. No. Here, here, and back here. Can you see that? That's one full cycle. So technically, if I really needed to, I could say this point to this point, that is also one wavelength. Okay? Okay? So yeah, many ways to look at a wavelength. It's really just one full complete cycle. Now, how do you use that? The wave equation is really used in this chapter and the next in EM spectrum. And the formula that you must remember is V is equals to F lambda. V is the speed of my wave. To find the speed of wave, right, one of the ways is using to find the frequency of the wave. How do I find the frequency? Frequency is found when I look at my displacement time graph. Right, one particle, consider my period, and transform it into frequency, right, using this formula here. Wavelength is found, well, over here in the displacement distance graph. Okay, please learn to be able to manipulate this, because sometimes they ask for F, sometimes they ask for lambda, sometimes they ask for V, so manipulate your formula accordingly. Okay, let's see what else. Take note of the units. Sometimes this wavelength could be in cm, sometimes it could be in meters. Just change your units accordingly. So this might be meters per second square, meters per second, or it could be cm per second. What's a wavefront? Number 4. Wavefront is really this imaginary line linking up all of my crest of the wave side by side. And the way we did it in class is to just imagine this 3D object, okay? And so what's behind it, what you can't see, would be what's over here, correct? This the behind part. So I want you to think of this thing over here as 3D. So let's use this one, and this one, correct? So this is up, this one over here is going up, this is going to the right, and this is going out. So if I have a wave here, and so the idea is that, let's say if I have many of these waves, but let me arrange it better. Okay, this one is here, this one is here. Okay, can you see it's like all the waves side by side? Okay, and then if I can join up all of those, all of the crest together, right? It's like this imaginary line joining up the crest. Can you see? So we have these lines. So this line over here is a wavefront that connects all of my crest, just like the water waves that we see. Okay, it's one way to remember it. The waves that you see, and at the top of those waves, well, we see this imaginary line connecting all of it together. Well, that's a wavefront. But the interesting thing is this, that if I can see a wavefront, what I'm actually looking at, if I look at one wavefront and the next wavefront, I'm actually looking from crest to crest. And if the idea is crest to crest, that actually means, right, I'm actually looking at a wavelength, correct? Because this is really a displacement distance graph, isn't it? Displacement distance. Can you see that? So in this graph, which is displacement distance, from here to here, that would actually be one wavelength. And most of the questions for wavefronts, where they actually give you all the different lines. So this is really 3D view, but usually what they will do is that they give you in terms of a top view, and all you see is just these two lines, really as if I'm looking from the top of this diagram and just see two lines. And when I see the two lines, I know, oh, these are wavefronts. Well, that's one wavelength. Okay, that's lambda already. And we use the idea for wavefront for lambda, maybe you can find my speed, if they give the frequency, so on and so forth. Right? Now, last but not least, so that I can end this below 18 minutes, the types of wave. There are two types of waves that you need to know. One is transverse, and one is longitudinal. Right? For transverse waves, but the idea is that both of them, yeah, they do transfer energy without transferring the medium, without transferring the particles themselves, without transfer of medium. But how they're different is that for transverse wave, the particle motion, see, we're going back to this thing up here, right? It comes on back to this part. Direction of wave versus direction of particle motion or vibration, right? In terms of transverse waves, if the direction of my wave is, well, this way, from left to right, my particle direction or vibration would be perpendicular. Perpendicular, right? So you need to compare. Direction of wave or wave motion is perpendicular to the direction of particle motion or particle vibration or just vibration, right? See, particles vibrate this way, wave motion goes this way, perpendicular. But for longitudinal waves, what happens is that if my wave is this direction, my particles are going to vibrate this way, are going to move this way, parallel. Okay, go back to your textbook and check this part out. But this is the main idea you should remember and should be able to explain. Well, that's the main difference. Well, over here we don't look at peaks and troughs anymore, but we consider in terms of compressions and rarefactions. So go refer to the worksheet concerning compressions and rarefactions, where you need to find how do you get like a wavelength. That means you basically look at the compressions to the next compression, that's one wavelength, or one rarefaction to the next rarefaction. Not as simple, but the easier one is actually you look at where the compressions are and then you compare it. Actually, that's basically about it. Alright, so please look through your worksheet materials. You should be able to get these 5 things. Anything, please let me know. But generally, this would be a quick recap of what waves are in just under 18 minutes. Alright. Okay, that's it for today. Take care, guys. Bye.